In this video, I'll teach you all the main concepts of Snowflake, including getting your first hands-on experience. This crash course has been designed for complete beginners, anyone who wants to learn Snowflake from the ground up. Whether you're a business user looking to understand Snowflake terminology or evaluate a vendor, or an engineer aiming to level up your data skills, by the end of this crash course you'll understand the fundamentals, get practical experience quickly, and gain the confidence to start working effectively with Snowflake from day one. We'll be dividing this hour-long course into 8 sections. We're going to start with a high-level explanation of what Snowflake is, looking at it from 3 perspectives I think are fundamental to getting a handle on Snowflake immediately. In this section, we'll also go through some of the common workloads Snowflake are trying to support, like data science and data engineering, looking at the features Snowflake have implemented to enable these workloads. We then go a step deeper and look at Snowflake's multi-cluster shared data architecture. We'll step through each of the architectural layers and get a sense of how they interact to return data when you submit a query. Next, we'll get hands-on and quickly set up a free Snowflake trial account so we can actually start using Snowflake. I promise it doesn't take long at all. We'll then have a whistle-stop tour of Snowflake's user interface, Snowsight. It's likely you'll spend a lot of time on the UI, so it's important we know where everything is. I'll also explain here in a bit more detail the various areas on the UI you can edit and run code. There is a bit of nuance here with the introduction of workspaces. We follow this up with a look at a fundamental part of how we work with Snowflake, objects. These are the constructs we interact with to enable so much of Snowflake's functionality, so it's really important we get them right. Then it's a deep dive into some of the most essential objects for managing data containers like databases and schemas, and the objects used to hold data, tables and views. We then zoom in on the table object, understanding its structure in a bit more depth, and how we use SQL to query a table's data to learn what we need to know. We then wrap things up with a closer look at the object that does the actual work of computing our query results, virtual warehouses. Here we'll get a high-level view of what a virtual warehouse is, how we configure their properties, and take a look at virtual warehouse state, which is crucial to understand if you want to control cost. Okay, so without further ado, let's kick things off. We'll first answer, what is Snowflake? To really understand what Snowflake is, I find it helpful to break it down into these 3 terms: a cloud-native data platform offered as a service. Each component of this definition is fundamental to understanding Snowflake and why it's become so popular. Let's explore what each of these terms mean, starting with data platform. As Snowflake gained popularity, the marketing and documentation surrounding it describes Snowflake as a cloud data warehouse, positioning itself as a predominantly analytics solution. However, Snowflake have gradually moved away from this description, now preferring the Snowflake platform or AI data cloud. This was done to underscore that Snowflake has been enhanced with capabilities beyond what you'd expect from a traditional data warehouse, and represents a convergence of various data technologies in one place. Although still firmly rooted in SQL, it now supports a range of languages and workloads, which this screen capture here hints at. Let's run through features from each of these workloads to give you a high-level sense of what Snowflake is. Snowflake's history as primarily a data warehouse is immediately felt when you use the platform. It uses the table data structure to store its data, and databases and schemas to organize that data. Also, one of Snowflake's main languages for managing data and objects is ANSI Standard SQL. And as we'll see in the next lecture, Snowflake's system architecture is also designed with data warehouse analytic jobs in mind, such as complex queries like ranking and rolling averages being executed across multiple tables. Snowflake also has many features to simplify steps in the data engineering lifecycle, like data ingestion, transformation, management, and governance. We have the copy into statement to bulk load data from files into tables, the Snowpipe serverless service that streams new files from cloud storage into Snowflake tables, stream objects to capture table changes, and task objects to schedule or trigger SQL logic to process those changes. We also have new managed features like OpenFlow and Managed dbt. OpenFlow is an integration service for ingesting and transforming data with connectors based on Apache NiFi, and Managed dbt is for running data transformation steps within Snowflake using dbt core. And across all of this, to remove the burden of an engineering team designing a bespoke security solution, Snowflake comes out of the box with many advanced security features, like encrypting all data at rest and in transit, role-based access control, multi-factor authentication, and more. Snowflake have also implemented a number of features you'd expect from a relational database. Along with ANSI standard SQL, all Snowflake SQL statements are ACID compliant, which are 4 database properties which guarantee strong support for transactions. Snowflake also supports high levels of concurrency without read-write locks, allowing multiple transactions to run simultaneously without interfering with each other. However, because Snowflake initially focused on analytical workloads, many relational database features were historically missing, like enforced referential integrity and low-latency single-row access. That's changed with Unistore, Snowflake's hybrid transactional analytical processing initiative, which introduces hybrid tables, a table type combining relational and analytical capabilities. We won't be going into Unistore in this course, but it's a good feature to be aware of. Snowflake also has many features you'd expect from a data lake. The Snowflake service can scale out storage and compute to handle big data in the petabytes. You can also store raw files without needing to specify the schema up front. Snowflake can also natively process semi-structured data formats such as JSON or Avro, with the ability to manipulate complex data structures using built-in functions and SQL extensions. You'll also sometimes see Snowflake referred to as a data lakehouse. This is because it blurs the line between warehouse and lake with its mix of features from both. You might even see Snowflake refer to themselves as an open data lakehouse. This is a reference to the fact they've implemented the Apache Iceberg open table format, so you can easily query data residing outside of Snowflake. There's also been a concerted effort to bring the power of large language models to Snowflake, even incorporating AI into the platform name. All the features making use of LLMs come under the umbrella term Cortex. This includes LLM functions, Snowflake Copilot, Document AI, Cortex Fine-Tuning, Cortex Search, and Cortex Analyst. There's also a new feature called Snowflake Intelligence, which allows you to build agents which make use of the Cortex features like Cortex Search and Cortex Analyst. We'll be getting hands-on with LLM functions later in the course. Snowpark is a library that lets you process Snowflake data using Python, Scala, and Java. We can use the preferred language for machine learning, Python, to perform machine learning tasks like training models. Snowflake also has native support for Streamlit, meaning we can create interactive machine learning and data science-powered web apps all inside Snowflake. We also have access to an end-to-end feature set to handle traditional predictive ML flows, like training models, storing features, and developing in a Jupyter-style environment with notebooks. There are loads more features in this space, and more are constantly being added. This is just a small sample. The last workload I'd like to talk about is data application development. Snowflake maintain many connectors and drivers for high-level languages like Python, .NET, and Go, and database connectors like JDBC and ODBC to help in building data-intensive applications. In Snowflake, you can extend the built-in functions with user-defined functions and stored procedures, which can be written using Java, JavaScript, Scala, Python, or SQL. So we can see Snowflake is trying to cover a lot of bases and is a little bit more than just a data warehouse. Let's look at another component of our definition, Snowflake as a cloud-native solution. All the software that allows Snowflake to handle the workloads we just went through was purpose-built for the cloud. It's not a retrofitted version of an existing technology like Hadoop or MySQL. This is a really important thing to understand. The vast majority of the software Snowflake has designed has been created from scratch to run on the cloud. The query engine, the storage file format, the metadata store, the caching, the architecture generally was designed with cloud infrastructure in mind. It's not what is called a cloud wash solution, which is a port of an older technology migrated to the cloud. The actual hardware, the storage, the compute, the load balancers, all the infrastructure that make up a single Snowflake account and runs the software Snowflake designed is provisioned into one of 3 leading cloud providers. It was originally designed to run on AWS and expanded to include Azure in 2018 and then to Google Cloud Platform in 2020. An account like the trial account we created exists in a single cloud provider's region. Because of this, Snowflake inherit the many benefits of the cloud. High availability, the ability to always have access to services and data. Scalability, so we can very easily add compute or storage resources. Elasticity, so we can dynamically scale out based on demand. Durability guarantees, so we know our data is replicated and it won't be lost, and many more. Okay, let's look at what software as a service means. Hosted services in the cloud can be provided in various delivery models. You could have virtual machines hosted remotely which are accessed and managed by a user, like EC2 instances in AWS. Snowflake is slightly different from that. It's a pure SaaS product or software as a service product. This means that as users, there is no management of our account infrastructure at all. There's also very limited management of software, with the only real thing to configure being Snowflake connectors like the SnowSQL command line tool. Snowflake do expose some settings to tune the behavior of the platform, but this is done indirectly by setting properties via SQL or on the UI. In Snowflake, the user performs no manual upgrades or patches to software. There are weekly online updates and patches which are completely transparent to the user and cause no visible downtime. As with many SaaS products, Snowflake offer a flexible pay-as-you-use subscription model. The flexibility of this model allows users to pay only for the resources that are needed and is therefore generally cheaper than large upfront capital expenditure costs required to set up your own hardware and software. But of course, as always, there are exceptions to this. Accessing Snowflake is really easy. No need to set up any software. You interact with a Snowflake account through the UI by authenticating with a username and passkey. This can optionally be extended with connectors and drivers for programmatic access, which we mentioned earlier. Optimizations like partitioning of data are done automatically, so there's no longer a need to specify things like static partitioning keys or indexes. These data optimization activities are done automatically as part of the loading process. So, I hope you now have a better understanding of what Snowflake is. In the next lecture, we'll get into the nuts and bolts of Snowflake's unique cloud-native architecture. See you there. One of the reasons Snowflake made such a big splash when it was released is because of what we're looking at here. This is Snowflake's unique architecture designed specifically for the cloud, what they call the multi-cluster shared data architecture. You can break Snowflake's internal services into 3 distinct architectural layers. What we call our Snowflake account is a collection of services from each of these layers. Down here is the centralized storage layer. This is where we store our table data organized into databases. When we create a Snowflake account, we select a cloud provider such as AWS or Azure, and as part of the provisioning process, we're allocated some cloud blob storage from that cloud provider. So if you were to create an account using AWS, under the hood, the storage layer would use the AWS S3 service. S3 is a type of blob storage and is really good at a few things. Scaling out almost infinitely to store truly huge amounts of data. It has strong availability guarantees, meaning it rarely ever goes down. And it has excellent durability guarantees, meaning data is replicated across geographic locations to ensure data is never lost. As Snowflake users, we inherit all of these native abilities. When we load a data file or insert some records into a Snowflake table, it's divided into small files Snowflake call micropartitions of about 50 to 500 megabytes in size and stored in our blob storage. The data in these micropartitions has been encrypted, compressed, and converted into Snowflake's proprietary columnar file format. In various ways, these changes make the types of OLAP queries we'll be running on Snowflake much more performant. Moving up a level, we have the query processing layer or compute layer. This consists of a huge pool of compute clusters managed by Snowflake, which they call virtual warehouses. In our account, we can create a virtual warehouse object using SQL, and behind the scenes, Snowflake will allocate one of those compute clusters to us or spin up a new one. They're responsible for performing the computation required to process a SQL query using the table data in the centralized storage layer. When we issue a SQL statement, we set which virtual warehouse to use. This virtual warehouse will then make a remote call to the storage layer and retrieve the raw table data, store it on a local high-speed cache, and compute our results. Virtual warehouses have a number of unique properties we'll see throughout the course. They can be created and dropped instantly. They can be paused or resumed. When resumed, they incur cost, and when paused, they don't. They also come in different sizes, which indicate their relative compute power. At the top, we have arguably the most interesting layer, cloud services. This is a layer of services written in Java that coordinates the whole show, hosting your account UI, handling authentication to your Snowflake account, managing the cloud infrastructure of the lower layers, parsing and optimizing SQL queries, storing metadata, and a lot more. Taken all together, this is what is called a service-oriented architecture, a collection of globally available services that Snowflake manages, constantly communicating via RESTful interfaces. For example, the physical nodes of the virtual warehouses are entirely separate from where we keep the long-term table data. They communicate over the network. This novel architecture is one of, if not the, main differentiators of Snowflake and allows for some quite unique capabilities. Firstly, storage, compute, and management services can now be scaled independently of one another. They're decoupled. Secondly, because the layers are decoupled and provisioned in a cloud environment, there is no hard limit on how much each layer can be scaled. We can throw as much data as we want into the cloud storage layer and scale out compute near infinitely. The multi-cluster aspect of the multi-cluster shared data architecture is the ability to create as many separate compute clusters as desired, and they'd be isolated from each other as different virtual warehouses. This allows for workload isolation, for example, allowing analytics and pipeline jobs not to contend for resources. Okay, that's it for an overview of the Snowflake architecture. Okay, let's provision ourselves a Snowflake trial account. This is so you can have a look around the UI and run some basic commands yourself. If you'd rather skip this stage, that's okay, you can just watch along. So as we've seen, Snowflake is a software as a service solution, which in Snowflake's case means they maintain a bunch of services like storage, compute, and management running across the three big cloud providers: Amazon Web Services, Google Cloud Platform, and Microsoft Azure. When we ask Snowflake for an account, they ring-fence a portion of existing services or spin up new ones and present that secure environment to us in the form of an account that we can log into over the internet. The Snowflake trial account is our own fully featured private sandbox in which we can ingest huge amounts of data and run a variety of languages to interrogate that data, including trusty ANSI standard SQL. We start things at the signup.snowflake.com page. From here, as it says, we can start our 30-day free trial. We'll fill out this first section with some basic information. Once complete, we now choose the edition and cloud provider for our trial account. There are 4 Snowflake editions: Standard, Enterprise, Business Critical, and VPS. The edition determines what Snowflake features you'll have available to you and to some extent how much it costs to use Snowflake. With each edition, you add to the previous edition's features. For example, in the Standard edition, all data at rest and in transit is encrypted, so therefore all higher editions have that as well. But say you wanted to use Snowflake's multi-cluster warehouse feature, well, that would only be available from the Enterprise edition and up. As it says, Enterprise is the most popular, as it's a good balance between features and cost. Let's keep Enterprise. As we saw before, the cloud provider determines the underlying resources Snowflake will use to host your account. For this crash course, we don't need to be overly concerned about which one we choose here. I'll be choosing AWS as it usually has the latest features. All your account infrastructure is provisioned into a single cloud provider's geographic region. This should default to the nearest region to you. In my case, that's Europe, London. Please select the region closest to you. Once we see this survey page, we know Snowflake has kicked off its automated process that will provision an account for us. After a few minutes, we'll get an email from Snowflake containing this activation button. Clicking this will redirect us to the welcome page for your account. We'll now need to create our initial user. Let's call it admin. Then please select a memorable password. We'll skip this prompt about how we want to start because we want to head straight to the home page to kick off our tour. So here we are in Snowflake's user interface, what they call Snowsight. The first thing I'll do is go down to the bottom left, click my username and change the theme from dark to light. Just so when you watch, we're not changing from the light theme lectures to a dark UI, but if you're following along, use the theme you'd prefer. So while we're down here, this part of Snowsight contains your user settings and some handy account info. We can set the default role, which determines what we're able to see and do on Snowsight. Next, we have an easy way to see our organization name and our account identifier. Then we have settings, which opens up a page to let us alter user details, change our passwords, select a default language, enroll in multi-factor authentication, and a lot more. Support is for managing support cases with Snowflake, so they can help with any issues you're having with your account. Appearance, which we've covered. Then we have Connect a tool to Snowflake. This opens up account information, really handy for connecting programmatically with tools like SnowSQL, which is their command line tool. We then have links to Snowflake connectors and the documentation, and the rest we don't really need to be too concerned with at this stage. Okay, so this is the home page. At the top is a search bar, which lets us search for objects in our account like tables and databases. We can also search the Snowflake Marketplace for data products. Quick actions are what they sound like, links to specific parts on the UI that let us perform specific tasks like uploading a file and creating a worksheet, which is one area we can run SQL. Projects give us quick access to areas we do the actual work of data engineering and analysis, things like notebooks, worksheets, which we'll have a look at in a second. On the left here, we have the navigation menu with all the features Snowflake has to offer, broken down under various headings. If we hover over projects, we can see a few subheadings. The most important for us are worksheets, notebooks, and workspaces. There's a little bit of complexity around worksheets and workspaces that we should clarify. Workspaces are a new addition to Snowsight, and they will eventually replace worksheets, but the two will still exist together for some time while people migrate. So what we'll do is take a quick look at worksheets now, but as we progress through the course, we'll be using workspaces to run our SQL. Workspaces are very similar to worksheets, but just have a few more features, but we'll look at that in a moment. Okay, let's head over to the worksheets page. If we go to the top right and click the drop-down, we'll see two options, Create SQL and Python worksheets. Let's first create a SQL worksheet. If we go to the tab at the top, we can rename this worksheet. Let's call it My First SQL Worksheet. On the left is the Object Browser. This is where we can see the databases and the objects they contain, those we have permissions to see. Let's expand the sample data database that comes automatically with every trial account. Don't worry too much if you don't see this, just watch for now. Inside we have schemas. I'll select one to reveal the tables this schema contains. In the middle here is the canvas. This is where we actually write our code. I'll select every record from this customer table by writing out select star from and then double-clicking the table I want. If we execute this by clicking the blue Run button, an interactive tabular result set will be shown in a pane at the bottom of the screen. We can go ahead and click around this result set and see some statistics on the right. Okay, let's head back to the main worksheets page. We can now see the worksheet we just created listed. Let's now create a Python worksheet. Rename it to My First Python Worksheet. We'll see it's very similar, but now we can use Snowpark Python code to interact with our data. Snowpark is a library developed by Snowflake so we can query our data in high-level programming languages like Java, Scala, and Python. So that's all we'll do on worksheets. They're good to know because they'll stick around for a bit, but the default development environment for SQL will soon be workspaces. So let's head over there and understand the difference. A workspace is a bit like a code editor like Visual Studio Code. Instead of Snowflake storing a standalone file you can run SQL from like a worksheet, a workspace is composed of a directory of files. That directory of files can contain SQL files which you can run just like a worksheet. However, it can also contain other files for a project. It's analogous to a Git repo. In fact, if we go up to My Workspace and click the drop-down, we can see Create Workspace from Git repository. This is a powerful new feature of workspaces. You can work on version control projects directly in Snowflake. Something like a dbt project that does data transformations can be tested, edited, and pushed back to Git, all from within a workspace. If we click Add New, we have the option to add a new SQL file. Let's call it test.sql. It will open up a tab on the right, which is essentially just like a worksheet. From here, we can run our SQL commands. Similar to IDEs, we can also split the screen to work on multiple files at once. The results show at the bottom, and the Object Explorer is in the bottom left. One last thing to mention for now is the Worksheets area. This is so we can run our worksheets in this new environment while people migrate to workspaces. We can even convert a worksheet by dragging it up to the workspace area. Okay, we'll explore workspaces in a lot more detail in a coming section where we start to run some SQL commands. Now it's time to head over to notebooks. If you've ever used Jupyter notebooks, they're very similar. Notebooks are an interactive cell-based programming environment for Python, SQL, and Markdown. Let's quickly create one with default settings to have a look at. You can see on the right the different cells which can be executed independently in different languages, all working on data stored in your account. This allows for some really interesting use cases, especially in the data science space. If I run this middle cell here, which has SQL code, it will spin up a virtual warehouse and we can have a look at the output. Okay, let's hover over our projects heading again and we can see 4 other features. Streamlit is for creating interactive web apps, primarily for data science use cases. Dashboard is for creating visualizations in Snowflake. App Packages is for accessing the Snowflake native app framework to deploy apps made of Snowflake functionality. Templates are basically pre-written notebooks or worksheets showing you how to do a variety of tasks from ingestion to sentiment analysis. So we don't have time to go through every heading in a lot of detail, and we also don't really need to, so I'll speed things up a bit now and call out some important areas. If we click on ingestion, it has some wizards and links to other areas of Snowsight and the documentation. It's all about getting data into Snowflake so we can process it. Transformation is comprised of all the Snowflake functionality for creating automated data pipelines. A relatively new addition which it opens up first is dbt projects. dbt was a third-party tool for creating SQL-based data pipelines, which Snowflake now natively supports. We also have dynamic tables and tasks for scheduling the execution of code. AI and ML now contains a lot of features, from the new class of LLM-based features known under the name of Snowflake Cortex, to the more traditional ML features like feature and model stores. Under monitoring, we can track system metrics which we can use to identify problems. An important capability, which is what we open up first on, is the query history. This provides statistics on all the queries we've executed in an account. More on that later. The marketplace is where we can go to find data products, data sets, apps, and more that we can really easily import into our account. The next section is categorized under the phrase Horizon Catalog. This is all about data governance, a central place we can go to understand what objects are in our accounts, manage users and roles, and manage how we share data with other Snowflake accounts. The last section here is called Manage. Here are some important aspects around the management of virtual warehouses, the compute clusters we use to execute code against our data. More on that later. Also, a really important section called Admin, which is all about managing and monitoring the expenditure of your account. From here, we get a dashboard covering credit usage of your account during a specified billing period, broken down by warehouse and queries. Okay, that was a lot of information. Don't worry too much if you're still a bit fuzzy on some aspects. We'll go into a lot more detail in later videos. For now, we'll take a step back and discuss a fundamental aspect of the Snowflake platform, objects. The principal interface for interacting with a Snowflake account is SQL. If you want to load data, transform data, analyze data, or configure account properties, the default and most deeply supported method of doing this is with SQL. There are other programming interfaces like Python and Java now which we can use too, but these are mostly for data processing specific tasks, not so much administrative ones. And as we saw, we also have the Snowsight UI, which lets us perform a lot of actions on our account through a nice visual interface. But if we want full control of our account and we want to automate these actions, we use SQL. Now, SQL commands are executed against objects. An object in Snowflake or any SQL database is simply something you can interact with, something you can issue commands against that enables a bit of functionality. For example, here's a command to create a new user. A user is an object in the Snowflake system, and running this command makes changes internally to allow another set of credentials to log into an account. Here's the command we ran in the worksheet, which selects all the rows from a table. A table is an object. And here's how we set the default time zone for an account. In this context, our account is an object. Snowflake objects fit into a hierarchy, with the objects of a lower layer being child objects of the layer above it. One account has multiple user objects, for example. You might recognize some of the classics in this diagram if you've used SQL before with tools like Postgres or MySQL. Objects like databases, schemas, and tables, they're building blocks of how we organize and store our data. We also have objects which are specific to Snowflake and enable a lot of its advanced features, things like streams, stages, and pipes. Okay, let's start from the top and work our way down. An organization is an interesting place to start and understand the nuances of what an object is. Although it's described as an object by Snowflake, we only really execute a small number of advanced SQL statements using the keyword organization when compared with a more straightforward object like table or user. It's really more of a special type of administrative Snowflake account where a business entity can manage one or more standard Snowflake accounts they own. Standard accounts like the trial account we created. Think about big multinational corporations. They might require loads of different Snowflake accounts on different cloud platforms and regions for different geographies, brands, or business units. In the Snowflake organization account, an organization administrator can manage accounts, for example, creating them, monitor accounts, and enable cross-account features like replication from one secure area. Going down a level, we get to the standard accounts which an organization can manage. A standard account is a private collection of services Snowflake ring-fence for our personal use, accessible via a unique URL. All newly created accounts exist within an organization, but using the organization features is optional as you might only need to use one account. The URL is a combination of an organization identifier and an account identifier, which you will have seen when logging into Snowsight. We may also use the word account to refer to an account object in Snowflake. This is used to change account properties and manage account-level objects via SQL like we saw in the previous slide. Each Snowflake account runs on a single cloud provider, AWS, Azure, or Google Cloud, which supplies the compute, storage, and services Snowflake uses. The account also lives in one geographic region within that cloud, determining where your data is physically stored, which regulations, features, and pricing apply, and how much network latency you'll experience. When created, an account is assigned a Snowflake edition, which can be changed later, and comes with several built-in roles for managing resources which we glimpse when going through Snowsight. For now, we'll be using the account admin role, which gives us wide-ranging permissions to manage account-level settings and objects. Just below the account object here, we have what are referred to as account-level objects. These typically don't hold data, but are used to configure different parts of your account, such as users and virtual warehouse compute clusters. Databases form the first main way we can organize our data stored in Snowflake. How we decide to split data between databases is driven by multiple factors, such as the business, technical, security, and regulatory needs of an organization. For example, data can be organized into separate databases based on the environment in which it's used, like development or production. One account can have many databases. One level down, databases can be further organized into schemas. Schemas are logical containers or namespaces within a database that allow for organizing related tables, views, and other database objects. One schema belongs to one database. Schemas themselves are comprised of many different types of objects, which serve a variety of purposes. Although they technically sit in a schema, they're most often referred to as database objects. One example is the view object, which is used to store a SQL select statement that can be shared between users. Arguably, the most important database object in this list is the table. The table is the logical representation of our stored data and is what we will be primarily interacting with. We'll pick back up with tables in our next lecture, where we break down more details around containers like databases and schemas and look at some of the types of tables and views. See you there. it's a good idea to get some facts under our belt about the important objects we're looking at here. Data container objects like databases and schemas, as well as two very common database objects, tables and views. This diagram shows a more zoomed-in version of the object hierarchy relevant to these objects. Let's take a closer look at the database container. The first thing to know is that databases must have a unique name in an account. Also, its name, more technically called an identifier, must start with an alphabetic character and cannot contain spaces or special characters, unless the entire identifier string is enclosed in double quotes. Identifiers enclosed in double quotes are case sensitive, those without are not. Let's run through a few sample commands showing a few ways we can create a database. This is the simplest command to create a database. In SQL, we create objects with the intuitively named create statement. The create statement is classified as a data definition statement or DDL statement, which you'll often hear it called. Databases can also be created from a clone of another database in the same account. This uses Snowflake's zero-copy cloning feature. Databases and their child objects can be replicated to another account. Databases can be created from a share object provided by another Snowflake account. And how about schema objects? Like a database, a schema identifier must be unique within a database. And again, like a database, a schema name must start with an alphabetic character and cannot contain spaces or special characters, unless the entire identifier string is enclosed in double quotes. The same case rules apply here. If wrapped in double quotes, the identifier is case sensitive. If it isn't wrapped in quotes, it's case insensitive. Here we have the DDL create statement for a schema. And this code snippet shows how schemas can also be cloned. This produces a mirrored version of a schema and its child objects. The database name and the schema name together form a namespace in Snowflake. You can prepend the namespace to a table name to globally refer to a table, or you set the namespace in the context on the UI, which we'll see in our next hands-on. So, let's take a look at the types of tables and views we get in Snowflake. Tables are a logical abstraction over the data in the storage layer. They describe the structure of your data in order for you to read from it. There are 6 types of tables in Snowflake, each with a different set of requirements around data retention. The first is the permanent table type. This is the default table type when a table is created and is the most commonly used. As the name implies, this table will exist until it's explicitly removed by a user. We'll learn how to remove a table later. Snowflake has 2 data protection features called time travel and failsafe. Each table type has different limitations when it comes to these features. The time travel retention period for a table is the duration of time we can go back and perform data restoration tasks like restoring a removed table. A permanent table can set the time travel retention period up to 90 days if we're on an Enterprise Edition or higher Snowflake account. If on the Standard Edition, the max is 1 day. Permanent tables can also access the non-configurable period of 7 days for failsafe, in which Snowflake can restore deleted data. The second type of table is the temporary table. A temporary table is for storing non-permanent transitory data. For example, a step in a complex ETL process storing the result of a select statement for downstream processing. A temporary table persists for the duration of a session. Once a session is over, the table data is completely purged from the system. Temporary tables have a max time travel retention period of 1 day, regardless of Snowflake edition. They also do not have a failsafe period. Once a session is over, the table data cannot be recovered by Snowflake. Transient tables are similar to permanent tables in that they exist until explicitly removed. However, they differ in that they have a max time travel retention period of 1 regardless of the Snowflake edition and do not have a failsafe period. Meaning if you accidentally delete data in a transient table and the 1-day time travel retention period has passed, Snowflake support cannot recover the table data. Table data in failsafe contributes to storage costs, so this is one reason we might use a transient table over a permanent table. External tables are interesting. They provide the ability to query data which resides outside of Snowflake, for example stored in an AWS S3 bucket. You can overlay a structure onto this data and Snowflake will record metadata about the files. External tables are read-only and are generally slower to return a result when queried. External tables do not support time travel or failsafe. There are two newer tables not required for the exam, but I'll touch on briefly, just so you're aware. Hybrid tables are designed to support transactional as well as analytical workloads. They store data in a row-based format, enabling fast inserts, updates, and deletes. And unlike other table types, they actually enforce table constraints like primary key, foreign key, and unique for better data integrity. There's a lot more detail to this table type, but is out of scope for this course. If you're interested, I've added a link to the Snowflake documentation for hybrid tables to this lecture. Iceberg tables allow Snowflake to work directly with data stored in the open Apache Iceberg table format, typically in external cloud storage such as AWS S3. You can read, insert, and manage data in Iceberg tables, whether Snowflake manages the metadata as a Snowflake catalog table or an external catalog like AWS Glue. Iceberg tables do not support time travel or failsafe, and query performance can vary depending on how data is partitioned and stored in the external location, but it's generally better than external tables. Snowflake views also come in several flavors. The first is the standard view and is what you might expect from a data warehouse. It's an object that stores a select statement definition, not any data. Here's some sample code creating a view. You give it a name and define a select statement. The select statement references a source table, and when someone reads the view, the data is retrieved from the source table. Because they don't store any data, standard views do not contribute to storage costs. And if the source table for a view is removed, reading the view returns an object does not exist error. One of the functions of a standard view is to restrict the contents of a table, revealing only a subset of the columns of a table or a subset of the rows. The select statement definition in a standard view can be read by anyone with the appropriate privileges. This is relevant because not all views allow this. Materialized views also store a select statement definition, but instead of not storing any of the data, the result of the select statement definition is actively maintained. Snowflake charges compute for the background process that periodically updates the view with the latest results of the defined select statement. This is why the materialized view is known as a serverless feature. It doesn't make use of the user-managed virtual warehouses to keep itself up to date. There's also additional storage costs to store the results. And lastly, for materialized views, they can be used to boost the performance of external tables. Both standard and materialized views can be designated as secure by adding the keyword secure to the view definition. One of the functions is that the select statement definition is only visible to authorized users. Some optimizations the Snowflake Query Optimizer performs may inadvertently expose data ordinarily hidden from users. Designating a view as secure will bypass these optimizations. It's a way to be more certain that sensitive data is not shown to the wrong audience. Because of this, however, a secure view might have worse performance. Okay, up next we head back to Snowsight and put some of these concepts into practice. We'll talk through the structure of a table and how we use that to interact with our data via SQL. Okay, here I am on the homepage of the Snowsight UI. Let's head over to our workspace. We'll rename our test.sql file to queryingatable.sql. I'll then go down and minimize the worksheet section and readjust the Database Explorer here to get a better look. So, with our newfound knowledge on objects, let's take a closer look at the Database Explorer. We have a list of databases that come with our account by default. Let's expand the sample data database. If you don't see this, don't worry, just watch along for this hands-on. This is the last lecture we'll be using the sample dataset. These schemas group the sample data by the size of the data they contain. We'll go with the smallest available, tpch_sf1, because it's quicker to retrieve results from a smaller dataset. When expanded, we can see it only contains tables. This is where schema-level objects will be shown, things like views and stage objects. If we hover over the table, we get a bit of high-level metadata about the table, like how many rows of data this table contains, and how much space, megabytes, gigabytes, and so on, the table takes up in the centralized storage layer for this account. Okay, the first thing we'll discuss is context. Context is the current active settings that determine what your SQL statements apply to. Let's say we want all the records from the customer table we just had a look at. If we run this, you can use the Control and Enter shortcut or Command and Enter if you're on a Mac to run a statement in the canvas. I'll just minimize the Query History tab as we don't need that right now. You can see from the result we get an error. Snowflake doesn't know which customer table you're referring to because table names only have to be unique in a schema, so there could be multiple tables with that name scattered throughout your account. I'll just increase the size of the page here so we can see the code a bit better. The namespace is a vital bit of context telling Snowflake which database and schema the schema-level object you're looking for is in. We can provide this inline every time we reference a table like this. Or the more standard way is we can set the namespace so it's picked up automatically with every subsequent SQL statement. We can execute the use command for a database and schema which will programmatically set the namespace portion of our context. If we then run that original select statement again, the one without the explicitly set namespace, it'll work because it now knows exactly where to find that table. We can see what is set and change the setting via the UI by going up to the top right of the canvas. Here you can see the databases and schemas available to us. This area contains all the available context to set. There are the role objects, which determine what objects you're allowed to interact with. For now, we'll stick with the account admin. And also the virtual warehouse objects we have active. This is the compute our SQL statements will use. In our next lecture, we'll take a closer look at how virtual warehouse objects work. Okay, let's take a closer look at the structure of a table object. A table is a pretty intuitive structure to understand. It holds instances of a real-world entity that the table is attempting to describe. An attribute of a table is defined by a column running down. For example, here we have a customer name, their address, which country they're from, etc. A row in a table represents a single instance of that entity, in this case, a single customer. We might also describe an intersection of a column and a row as a cell. Now let's run the describe command. This returns the structure of a table object without the data and provides metadata about the type of data stored in each column. The first is the name of the column. Next is the data type. Data types are a really important concept because they not only give helpful information about what is in a column, but also enforces the type of data that can go in a given column. There are many different data types, and I'll put a more comprehensive list on the screen now. It covers things like strings of text, numbers, geographies, and date and time. And what is the purpose of defining one of these data types? There are a number of reasons. One is for internal storage and retrieval performance. It's easier to compress data which is all of the same type on disk, for example. Another is so we can use specialized functions on that column. For example, on a date column, we can calculate the difference between two dates using Snowflake's dateDiff function. Okay, you can also set a number of constraints on a table. These are bits of metadata helping others understand the data stored in this table. Like whether a column value should be unique, or whether a column should have a default value if no value is added to that column. Let's zoom in on the select statement, also called a query in SQL. We'll go deeper into queries and other SQL statements in our next section, but for now, let's join what we know about the structure of a table to how we'd functionally interact with it. In this query, instead of using a star indicating we want every column, we can explicitly set the columns we want. If we want to return only a certain number of rows, we can use the limit subclause. This only returns the first n number of rows from a table. Okay, up next we go into more detail on virtual warehouse objects, covering the unique ways they work to convert our SQL text into a result set. A virtual warehouse is an account-level object which represents a massively parallel processing compute cluster that Snowflake manages under the hood. We don't have access to any of the nodes which make up this compute cluster, we only interact with the object in Snowflake. This is the command to create a virtual warehouse object. In its most basic form, there is only one required parameter, the object identifier, which in this case we're setting to my first warehouse. As we touched on in the hands-on, a virtual warehouse is a vital bit of context we need to have active in our Snowflake environment to run SQL statements that require compute resources. Like the database and schema objects, we execute the use statement to programmatically tell Snowflake which virtual warehouse we want subsequent statements to use. Let's run through the basic flow of using a virtual warehouse. A virtual warehouse is required when you run one of these types of SQL statements: a select statement, data manipulation language statement such as updating rows in a table with delete, insert, or update, loading data into tables with the copy into table statement, or unloading data from tables with copy into location. It will execute these commands on the specific virtual warehouse set in the session's context. If we ran a select statement, for example, the virtual warehouse, as part of executing the statement, will retrieve the relevant data for the query from the centralized storage layer, store it on local fast SSD storage, also called the warehouse cache, perform the required computations to answer the question, and then return that to the user. Some commands which only act on metadata don't require a user-managed virtual warehouse set in the context to execute. For example, running the create and use commands don't require a virtual warehouse to execute. Users in an account can create and remove a virtually unlimited number of these warehouses instantly in a Snowflake account. This could be for different departments in a company or for different workloads, think ingestion versus analysis. And because Snowflake is ACID compliant, all this is achieved with consistent reads and writes to the centralized storage layer. Okay, there are two important concepts to be aware of. The first is the virtual warehouse size. That create warehouse statement used the default warehouse size, which is extra small, the smallest size a warehouse can be. We can explicitly set the size parameter like this. Snowflake has 10 t-shirt sizes. T-shirt sizing is a relative estimation technique to indicate the relative power of the underlying compute clusters and the servers that comprise them. Extra small has the least underlying resources available to it in terms of CPU, memory, and storage, and 6x having the most. Each size increase approximately doubles the underlying compute resources. In theory, because bigger t-shirt size virtual warehouses have more compute power, the faster the queries using that warehouse will run. However, this is only a very general rule of thumb. If you do a simple query on a small table, you won't likely see a performance benefit increasing the size of a virtual warehouse. Conversely, if you're running a very complex query on a very large dataset, you might see considerable performance benefit in sizing up. It does beg the question, how do you decide what size is right for you if you don't really have a good understanding of what the underlying compute resources are in terms of memory, CPU, and disk? Here, Snowflake recommends running some representative queries of a typical workload, say on an extra small warehouse. If they run in an acceptable time, then great. If they don't, try sizing up and all subsequent queries will run on the larger size. The second concept to know is the virtual warehouse state. Virtual warehouses can be in 3 states: started, suspended, or resizing. Started indicates that a virtual warehouse is currently active and it's ready to process queries. In this state, the virtual warehouse costs to run. The opposite of this is suspended. The virtual warehouse is shut down and is no longer costing anything. A warehouse can be resized up or down at any time, even while running queries. The resizing status indicates when this process is currently in progress. You can check the warehouse state by running a show warehouses command and checking the output column state. And using this, we can also see the size. By default, when a warehouse is created, it's automatically in the started state. Let's go on a quick detour on warehouse billing to understand why this is significant. Snowflake will charge a certain number of what Snowflake call credits per second a warehouse is in the started state, regardless of whether it's processing queries. Each warehouse size has a number of credits associated with it. What we're looking at here is a screen grab from Snowflake's documentation showing this. And depending on your account's region and cloud platform, a credit will equate to a different dollar value. Here we're contrasting credit values of the regions London and Seoul for AWS accounts. So, what you need to remember here is that the larger the warehouse size and the longer it's in the started state, the more you'll be charged. You can manually suspend and resume a virtual warehouse by issuing the alter warehouse command. The alter command is for changing object properties and parameters. Running a suspend warehouse command like the one we see here removes all compute nodes from a warehouse. This will put the warehouse into a suspended state after any queries currently executing are completed. And here is the command to do the opposite: resume a warehouse, putting it back into the started state. The key benefit of this functionality is to avoid paying for compute resources when they sit idle. For example, if you know you'll only be querying during 9 to 5 business hours, a user could suspend a warehouse at the end of the day and avoid being billed overnight. However, manually executing SQL statements isn't really in the spirit of automation. There are 3 virtual warehouse parameters available to us that control the suspend and resume behavior in an automated way. The first is auto-suspend. Auto-suspend specifies the number of seconds of inactivity, so not having any queries using it, after which a warehouse is automatically suspended. By default, when creating a warehouse, auto-suspend is enabled and is set to 600 seconds, so 10 minutes of inactivity. It might be tempting to set this as low as possible at any opportunity to avoid paying for compute when it's not required. However, there's a few caveats to bear in mind. A virtual warehouse cache is cleared when an instance is stopped. Therefore, queries could take longer when resumed. Depending on the size, provisioning of a virtual warehouse may take a couple of seconds, which will be added to the execution time next time you want to run a query. Next up is auto-resume. This parameter specifies whether to automatically resume a suspended warehouse when a query is submitted to it. If set to true, a warehouse effectively wakes up if a query uses it while it's in the suspended state. By default, auto-suspend is turned on. This can be turned off if you'd like to control costs and instead manually resume the warehouse only when it's required. Lastly here we have initially suspend. This indicates whether the warehouse is created initially in the suspended state. As we've seen, the default behavior when created is to put a warehouse in the started state. This would reverse that. You might use this if you want a virtual warehouse to not immediately start billing if all you want to do initially is to create a few tables, an activity which doesn't require a running virtual warehouse. This property will ensure it starts in the suspended state. Okay, so that's it. Well done if you made it this far. I hope you now have a much better understanding of what Snowflake is. We covered quite a lot in this hour-long crash course. We got hands-on, we saw the Snowflake architecture, important objects, ran queries, understood what virtual warehouses are. But it was only an hour and there's only so much we can cover. If you do want to learn more, I also have a much more comprehensive course on Udemy, which condenses a lot of the essential Snowflake information down into one place. We go into much more detail on Snowflake features and architecture, including a closer look at Snowflake's LLM capabilities. We look at account access and security, performance improvements, data loading, basically a lot of very important topics to know if you want to master Snowflake. It also covers everything you need to pass the Associate Platform or SnowPro Core Snowflake certifications. All of this is delivered by me, Tom Bailey. If you want to reach out, message me here on YouTube, LinkedIn, or Udemy. Thank you and see you soon.